In the second part of this module, we're going to be talking about logarithms. A logarithm is the inverse of an exponential function. A logarithm is asking the question, what power of the base would give me the answer? The logarithm is written in the form of log base A of b equals m. A logarithm can be any base, but the most common bases are e and 10. A log with base 10 is called a common log and represented by the word log with no base showing. A log with base e is called a natural log and is represented by ln with no base showing. Logarithms have many uses, including the Richter scale for earthquakes, decibel levels of sound, the brightness of stars, and pH balance. We are being asked to evaluate logarithms using a calculator. We are again going to round to the thousandth or the third decimal place. Our first problem is the common log of the cube root of 6. When you want to do a common log on your calculator, you want to use the key right here that says log on it. After pressing the log key, this is what you should see on your screen. To do a cube root, you want to use the caret key, and the cube root is this symbol right above the caret key. To do the cube root, you should hit the 3 and then the second and the caret key, and you should get what you see on your screen now. Complete the cube root by putting in the 6 and then closing the parentheses for the argument of the logarithm. Hit the enter or equals key, and this should show on your screen. So we now know that the logarithm, the common logarithm specifically, of the cube root of 6 is approximately 0.259, rounding to the third decimal place, which is the thousandth. On this problem, to do it on your calculator, you're going to hit your common log key. So it will say log and open a parentheses, and then you're going to just put in 25 divided by 3. When you do that and hit your enter, and then round to your third decimal place, you should be getting 0.921. To do the natural log of 2.31, we're going to use the key that says ln on it. It's right below the common log key. When you type that into your calculator, you should get ln with an open parentheses, put in the argument of 2.31, close your parentheses, and you should be getting 0.837 when you round to the third decimal place. You must be able to convert between a logarithmic equation and an exponential equation. And we do that based on this following definition, that the log base A of C equals B will be true if and only if A to the B equals C. So what I want you to note is that A is the base of the logarithm. When you go to the alternate form, it is also the base of the exponent. What was the original answer becomes the power on the exponential form. And then the argument equals the answer when you go from logarithm to exponential. On example 5, we are being asked to convert the expression we are given to the opposite notation. These first 4 are all in logarithmic notation, so we want to go to exponential notation. In order to do that, the base becomes the base of the exponent. The answer becomes the power, and then the argument, which is the 25, becomes the answer. Look at that. Do you get a true statement? 5 squared equals 25? Yeah, that's true. On the second one, base of the logarithm becomes the base of the exponent. Answer becomes the power equals the argument of the logarithm. Again, we got a true statement. On C, base of the logarithm is 4 to the answer is 0 equals the argument of the logarithm 1. Does 4 to the 0 equal 1? Yep. On the last one, base to the answer equals 1 over 81. If you did your exponent rules and checked on this, you would see that this too is a true statement. The next 3 examples go from exponential form to logarithmic form. So when we have 8 to the 0 equals 1, and we want to write that as a logarithm. First, we start with the word log. The base of our exponent becomes the base of our logarithm. The answer becomes the argument equals the power is the answer. On the second one, start with the word log. Your base is 7. Answer becomes the argument. Power becomes the answer. And on G, start with the word log. Base is 5. Argument is 1 over 125 equals the power -3. The next problem are a mixture of going from logarithm to exponent and vice versa, but all of these involve natural logs. So on H, when you have natural log of 9 equals y, the base of natural log is automatically e, which means when I go from logarithm form to exponential form, the base of my exponent needs to be e. The answer of logarithm form is your power, and the argument of logarithm form is the answer. On the next one, it's in exponential form, we need to go to logarithm form. Because the base of the exponent is an e, I know automatically that I want a natural log. My argument is the answer of exponential form, and then the power of exponential form becomes the answer in logarithm form. On J, we're back in log form. We want to go to exponential form. Because it's natural log, my base is e, my power will be 12, equals the argument of x. And then on K, because it's an e base, I want a natural log of the number 2 equals the power of the exponential form, which is y. On example 6, we're going to evaluate the expression. That means we need to give some kind of a numerical answer to the expression. In order to do that, we're going to ask ourselves, what power of the base gives me the argument? So on A, when we have log base 3 of 1/9, what power of 3 would give me an answer of 1/9? Well, the 9 is the power of 3, that's 2, but it's in the denominator. So because it's not a whole number, it's in a fraction, that tells me that this was originally a -2 power. On B, what power of 5 gives you an answer of 25? Well, it's 5 squared, so your answer is 2. On C, what power of 7 gives you an answer of 7? 7 to the first equals 7, so the answer is 1. On D, what power of 1/2 gives you an answer of 1? Anytime your answer is 1, your power had to be 0. We're being asked to use our given graph to translate the graph. So we are going back and using the translation ideas that we learned a while back, and we're applying them to logarithms. On the first example, we are given the graph of y equals the natural log of x. We're being asked to translate it to y equals the natural log of the quantity x minus 3 plus 2. So remember, when the number is being added or subtracted inside the function, that is a right or left motion. So the minus 3 is a right 3. The plus 2 tells us to take the whole graph and move it up 2. When we do these motions, the asymptote also has to move either right or left the way the rest of the graph is. In our given graph, the asymptote is at x equals 0, or the y-axis. That entire asymptote needs to move right 3. So it's now going to go through x equals 3. Now look for points that you can tell exactly where they are so that we can move those points the right 3 and up 2. We can tell that the point 1, 0 is on our graph. So we need to move that right 3 up 2. If you look closely, you can see that the point at 3, 1 is on your graph. So we're going to go right 3 up 2. So we know we have a curve going here, and we know we need to get closer and closer to the asymptote and not touch it. So this is the translated version of the given graph. This time we are given the graph of y equals log base 2 of x, and we are to translate it to y equals log base 2 of the quantity x plus 2 minus 1. The inside the quantity is a right-left motion. Since this is a plus, that means we need to go left 2. The minus 1 tacked on the end tells me I need to go down 1. My asymptote also needs to move the right or left, in this case, left 2. The current asymptote is the y-axis, x equals 0, so we need to go left 2 and have a vertical asymptote through x equals negative 2. We have a point at 1, 0. We need to go left 2 and down 1 for that new point. We also go through the point 2, 1. Let's take that point and move it left 2, down 1. So here's the curve of our new graph, and then get closer and closer to the asymptote and don't touch, and there's the translated version of the graph. Because of how logarithms are defined, we know that the following statements are always true. Log base a of a equals 1. If the base and the argument are the same, your answer will always be 1. On the second statement, log base a of 1 equals 0. Anytime your argument is 1, it doesn't matter what the base is. What power gives you an answer of 1? That's always 0. We have properties of logarithms that are true for any logarithm. It does not matter what base of logarithm it is. The first is the log of a product. If you are doing a logarithm and your argument contains a product, two items multiplied together, you can split that into the same logarithm you had originally that you separate into the log of the first item plus the log of the second item. When you have division in your argument, this can be split into the log of the numerator minus the log of the denominator. The logarithm must stay the same base when you spread it out into addition or subtraction. The last property we're going to look at is the logarithm when you have a power on your argument. If there is a power on your argument, you can drop that to the front and it becomes a coefficient of the logarithm. In our next problems, we're going to use these logarithm properties that we just talked about and fill in the blank. So we are being given on the first problem the log base 8 of 9 minus the log base 8 of 5. We had a property that says if you have subtraction between your logarithms, then you can change it into a single logarithm with division, where the first argument becomes the numerator and the second argument becomes the denominator. Our next problem, we have the log base 5 of 11 plus the log base 5 of blank equals the log base 5 of 88. Our property says that if we have separate logarithms that are being added, that converts to a single logarithm that is the product of the originals. So 11 times what equals 88? Well, it's 8. So our blank needs to be filled in with 8. We're going to use the properties of logarithms to evaluate the expression. And the word evaluate means you need to have a numerical answer. On our first problem, we have 2 times the log base 12 of 4 plus the log base 12 of 9. On that very first term, we have a coefficient. And our logarithm property says that a coefficient started as an exponent. So the first term gets rewritten as log base 12 of 4 squared. We're going to leave the second term alone right now. I know that 4 squared equals 16, so I'm going to rewrite this as log base 12 of 16 plus the log base 12 of 9. When we have addition between separate logarithms that are the same, we can change that into a single logarithm of the two arguments multiplied. So it becomes log base 12 of 16 times 9. But 16 times 9 is 144. So now we have to ask ourselves, to get a numerical answer for this, what power of 12 gives me an answer of 144? Well, 12 squared is 144. So my answer is 2. On this problem, we're going to use the idea that we have powers on our arguments and we're going to drop them to the front to become coefficients. So my first term will become 5 times the natural log of e minus the second term becomes 16 times the natural log of e. Now we're going to use the property that says when your base and your argument are the same, that equals 1. So this equals 1. This equals 1. So we are left with 5 minus 16, which gives us negative 9. Next, we're going to use the properties of logarithms to expand the expression. These will all be variable logarithmic expressions, so you will not have numerical answers for the most part. On this first one, we have a logarithm that's base 10, and in the argument, we have division. That means that we are going to separate it into log base 10 of the numerator, x cubed, minus log base 10 of the denominator, y. We are not complete until any exponents have been dropped to the front as coefficients. So the first term will become 3 times log base 10 of x. Second term stays the same as log base 10 of y. For our second example, we have log base 3 of the argument x squared times y. So here we're going to use the other rule that says when you have multiplication in your argument, you split it into separate logarithms using the same base and add the two logarithms, splitting the arguments. So log base 3 of x squared y becomes log base 3 of x squared plus log base 3 of y. The problem is not complete until any exponents on arguments get dropped to the front, and we have that on the first term. First term will become 2 log base 3 of x. Second term has no exponent, so it stays log base 3 of y. On example 11, we're going in reverse. We will be given expressions that have been expanded, and we want to go backwards and write the expression as a single logarithm. So on our first example, we have 2 times log base 5 of x plus 4 times the quantity of log base 5w minus 5 log base 5 of z. First, you need to note that because this 4 is outside the parentheses, it needs to be distributed to both terms. So our first term, we're not going to do anything right now. We're going to leave it as 2 log base 5 of x. Distributing our 4, we're going to have plus 4 log base 5 of w minus 20 log base 5 of z. All those numbers that are on the front as coefficients need to become powers of the argument. So our first term becomes log base 5 of x squared plus our second term becomes log base 5 of w to the 4th minus the third term becomes log base 5 of z to the 20th. Now, anything that has been added needs to be multiplied, and any terms that are being subtracted needs to become division. This then will become a single logarithm of base 5. The items that were added are x squared and w to the 4th, so they become multiplication, divided by the item that was being subtracted was the z to the 20th. The instructions are the same for this problem. The only difference is that one of our coefficients is a fraction. Our first term then will become log base 3 of y to the 1/5 power. Our second term, moving that coefficient up, will become log base 3 of w squared. And the last term does not have a coefficient, so it's going to stay as is, log base 3 of z. Anything that has been added as separate logarithm becomes multiplication. So we have a single logarithm now where we have y to the 1/5 times w squared. And any logarithms that have been subtracted, the argument is divided. So it's divided by z. The one other thing you can do is recognize that y to the 1/5 is the same thing as the 5th root of y times w squared over z. We need to have a way of evaluating logarithms that are not on our calculator. So to do this, we use what's called the change of base property. The change of base property says if you have log base a of the argument b, that is equal to the log base c, changed to a new base of the old argument over log base c, the new base, of the old base. We're going to put this change of base property into practice and evaluate some logarithms by using change of base. Our first example is log base 2 of 7. On our calculator, we have two choices. We can use the common log of base 10 or the natural log of base e. Either one works. It does not matter which one you choose. I'm going to show you first by doing the common log. If we do the common log for this problem, we would have common log of the old argument over the common log of the old base. So we would have log base 10 of 7 over log base 10 of 2. If you do this on your calculator, you get 2.807. You can also do this with the natural log. The technique stays the same. You do the natural log of the old argument over natural log of the old base. So we would have natural log of 7 over natural log of 2, and doing that on your calculator, you get exactly the same answer. So you have your choice. It does not matter which one you use. On our second example of log base 1/3 of 10, you have your choice. You can do common log or natural log. I'm going to write them both out so you can see what they would look like. With common log, you would have log of the old argument 10 over log of the old base 1/3. With natural log, you would have natural log of the old argument 10 over natural log of the old base 1/3. Putting that into your calculator, you should get negative 2.096.